Hello, everyone. Welcome to this Academy for Teachers masterclass on the wonderful weirdness of quantum theory with Dr. David Kaiser. I'm Ben DiNardo, and I've been teaching science for the last 21 years at the Birchwathen Lennox School. I love what I do because it allows me to interact with the next generation on a daily basis and hopefully help them learn some of the weird and wonderful things that make this world work. I'm a proud fellow of the Academy for Teachers, an organization that celebrates the incredible work that we as teachers do each and every day and provides us with inspiring and intellectually stimulating classes like this one. I don't know of another organization like it. I have the honor of introducing Dr. Kaiser. David Kaiser is a professor of physics and history of science at MIT. He is the author of multiple award-winning books, and his articles have been published in Science, Nature, the New York Times, and the New Yorker. When I saw this masterclass, I thought of the advice I give my own students when teaching quantum theory. If you think you understand it, you don't. If you think it's probably wrong, you're getting there. If you are convinced that it cannot be right, then you have a good understanding of the material. I'm hoping that Dr. Kaiser can get all of us further into that last group. However, David is not the only star of this masterclass. It is also my honor to introduce the 12 teachers here today who have been selected from many applicants. This is an impressive group with advanced degrees in chemistry, education, instructional technology, and physics. We teach grades 6 through 12 and early college at public, private, and in charter schools. Although most of us teach math and science, from astronomy and calculus to chemistry, living environment, and of course physics, we also have among us a teacher of composition and world literature. We also mentor more students through clubs and sports that range from a comedy ensemble, the LGBTQ club, Science Olympiad, volleyball, and that's just naming a few. There's an incredible amount of teaching experience here today. We've been in the classroom between 2 and 28 years. The total number of years we've been teaching is 172. We teach between 50 and 150 students. The number of children who know our names is 1,187, and that's this year alone. So your real audience today, David, are those 1,187 kids, because every teacher here will in some way share with them what we learned from you. And we will continue to share this knowledge with the 1,200 students we have next year, and the next year, and the year after that. Like quantum theory, the entanglements of this class may have a spooky added distance effect that, like neutrinos, spread beyond what can be easily measured. Thank you, Dr. Kaiser, for being here. Thanks to my fellow teachers for teaching. And with that, let the masterclass begin. David, the Zoom floor is yours.
Great, Ben. Thank you so much. I just want to thank Sam and Renee and Rachel for all their for the invitation and all their help along the way. And Ben, that was just a wonderful introduction. Thank you so much. And I'm really just delighted to be here. I'm going to go ahead and share screen, and hopefully everyone will see that okay. Quick thumbs up. That looks like it's okay. Great. Thank you. So this is the first session, and I'm really excited to share with you a subset, some portion of ideas about this wonderful weirdness of quantum theory, and in particular, not just some old ideas, many of which I think will be familiar, at least to many of you, but also some much more recent experimental tests or ways to try to zero in on some of these strange sounding ideas and make sure we're understanding the way the world works as carefully and cleverly as we can. But I actually want to start by thanking each of you very much in the spirit that Ben was mentioning. You know, a large part of why I'm able to do a lot of what I do is because I had a really amazing high school physics teacher. And I think about Michael Lawrence a lot. I was telling the folks in my little breakout room, I grew up in northern New Jersey, West Orange, very close to Ridgewood, where Anjali is. And Michael taught in the public schools there for 40 years. He retired a couple of years ago. I had him relatively early in his career. He'd been teaching maybe a dozen years by the time I had him in 11th and 12th grade, including for AP Physics. And not only was he an inspiring and engaging teacher who clearly loved the material, as I think I'm confident each of you are as well, but he would go the extra mile, not just with me, with a whole gaggle of students. And in my case, I remember as if it just happened. He loaned to me at one point, maybe just to shut me up. I don't really know, because I kept pestering him with questions. But he loaned me his own copy of one of his college textbooks, this well-known book. Some of you might have seen it, Iceberg and Resnick. It's a brick. It's 700 pages. And he let me borrow his copy, and I took it home. It was on my nightstand for weeks and weeks and weeks. I would stay up way too late trying to read it. I will not pretend to any of you that I understood anything I was reading. That wasn't the point. And I think Michael knew that. It was just to help point me in the direction that there is a lot out there and that we can try. And so what I learned from this experience, in addition to studying for my AP physics exam and the things that he was so gifted in shepherding us through, but I learned a kind of self-confidence that there are big, hard, weird sounding questions, and it's okay to ask about them. And there are tools to start the journey. And he also shared with me a kind of preview, a wider horizon than merely northern New Jersey, but a whole universe out there that really could be pretty cool to explore. And so I think about the impact that Michael had on my life and on generations. I've taught students at MIT who had come up from his physics classroom after I was a student there. In between, I know I have some indication of the kind of impact that each of you already have and will continue to have. So I just want to start actually by thanking each of you and the organization for bringing us together in this setting. We've already covered this stuff. Renee is so far ahead of me. So I had some little logistics here about the sort of question breaks and so on. I will pause the slides at a few spots. So hopefully we'll have time. I'll stop sharing screen at those moments. We can talk informally for a few minutes and I'll jump back in. If you do have a pressing question that's sort of right on that very moment, then please feel free to put it in the chat. And I think Renee can kind of monitor that and jump in if we need. But don't worry, I will actually pause as well for a bit more informal breaks along the way. So those are the preliminaries. I want to launch in now and tell you about a quantum adventure, actually a few quantum adventures that I've been really very, very lucky to get to participate in the recent years. They've allowed me to work with some really quite extraordinary colleagues and students, including international teams from many parts of the world. We got to use instrumentation that was both hulking and massive and buried deep underground, like these 5,000-ton detectors in an old mine, as well as some of these absolutely incredible telescopes up on a mountaintop in the Canary Islands. For that telescope test, we were gathering light from some of the most distant galaxies in the known universe, really exploring well beyond northern Jersey. I finally broke out. And we were using these tools to try to ask some of these questions which were recognizable to some of the physicists who'd come before, stretching back nearly 100 years. So we're trying to clarify or keep pressing on some questions that are not new, although we have newer tools and techniques to come to those questions. And that really is what I still find really very, very exciting. So for today's presentation, it's going to have three main sections with some breaks in between. I'm going to start with a review. This will very likely be familiar, at least to most of you, maybe not to all of you. But I still think it's worth just sort of sitting with some of this material and maybe taking a look at it with fresher eyes. And some of the conceptual features I want to focus on or remind us about are the key roles played by probability and by superposition in quantum theory. And I'll say, of course, plenty more about each of those. And then for next week's session, the main kind of concept we'll focus on is quantum entanglement. We'll get to that next time. After this first section, I'll break. We'll have some time for discussion. And then for the second main part, today we'll talk about Schrödinger's cat. Again, likely familiar to many or most of you. I'll try to talk a bit about where the Schrödinger's cat thought experiment comes from. What was Schrödinger thinking about at the time? Who was he talking with, and so on? A little bit of historical framing, and then talk about some things that I didn't know about until recent years. They're not often taught in our quantum mechanics courses, which is some very clever ideas to try to test this notion of Schrödinger's cat in real world scenarios. And then we'll break again, have a chance for some discussion. And for the last part today, I'll talk about this neutrino test, which was just super fun. And neutrinos, I think, are pretty amazing, enigmatic particles, and we'll talk a bit about those, and then how my friends and colleagues and I use those as a way to test Schrödinger's cat. So that's what we're doing for today, and then next week, entanglement. So we're going to hit some pretty strange ideas that, again, as Ben was reminding us, might make us dizzy or uncomfortable or skeptical or who knows what. So I always find it helpful to start by reminding myself, and hopefully some colleagues and students, that quantum theory is pretty amazing. It's worth hanging in there, even if some things sound preposterous. So as you know, quantum theory describes how matter behaves at the size of atoms and parts of atoms, even multiple atoms, molecules, essential for many ideas in chemistry. It's not just helpful, it is the single most precise scientific theory in human history. Let's give it its due, all right? It might make our head hurt, but come on, like, let's stick with it. There are some quantities, some properties of matter for which theorists can calculate in advance from first principles, and colleagues like Professor Gabrielsi at Harvard and his group can perform experiments on real physical materials and compare, and the theoretical prediction and the experimental results will match to 12 decimal places. There's not another element that I'm aware of in any area of human inquiry that can boast that kind of accuracy. So it has some price, some conceptual things we have to sit with and try to clarify, but boy, is the payoff pretty impressive. So for example, this example that I never tire of describing, if we put an electron in a magnetic field, we can characterize, quantify how it will respond to the magnetic field with a property that we call the magnetic moment. And the details aren't too important. We can talk about it if you want. But the idea is, using the principles of quantum theory over decades, not right away, the community learned how to calculate from first principles what the electron's magnetic moment should be like. Stick an electron in a magnetic field, how it will characterize its response. You can calculate out to 15 decimal places if you have literally nothing else to do with your day, or multiple days and months. Then people like Professor Gabriels and his groups can experiment on real electrons in actual magnetic fields and measure the magnetic moment. And you can do a quick comparison, and the mismatch is in parts per trillion. Let's just pause on that. That's like being able to predict in advance, strictly theoretically, the distance between one shingle on the roof of MIT's famous dome and a particular rock in a particular crater on the moon, and get the answer right to within the width of a single human hair. That's what parts per trillion is like. That's why I think it's worth slogging through what otherwise can seem frustrating or strange or just a little weird. Quantum theory is weird, but it also is wonderful. So now we'll get to some part that, again, is likely familiar, at least for many of you. Almost 100 years ago, actually in January of 1926, the Viennese physicist Erwin Schrödinger developed a new approach to quantum theory. Quantum theory had already existed, a patchwork of ideas, but he really introduced a new approach. And it was centered around what we now call the quantum wave function, or sometimes the Schrödinger wave function, and often given the Greek letter psi. There's a mathematical function that really does behave, if we plot it, like a wave. It will have peaks and valleys, crests and troughs. It can peak in one place but have a minimum somewhere else. What Schrödinger recognized pretty quickly was that these solutions to his wave equation, these wave functions, obey a property called superposition. That's just a fancy way of saying that you have two different functions that are each solutions to the equations, two separate wave functions. You add them together, and that new function will also be a solution. We can add or subtract these solutions and still have a valid solution. That's all superposition means. We could superimpose two different solutions on each other, and that will itself be a solution to the quantum equations. And that might not sound very remarkable, but that's what gives rise to these kind of classic wave-like behaviors, like interference. So if you have two waves, psi1 and psi2, which happen to have a crest around the same, say, location in space, the sum, which is also a proper solution, will have an even higher peak there. That's a constructive interference, or they can nearly wash each other out in destructive interference. So the superposition was a property of these quantum wave functions that Schrödinger himself recognized right away. It wasn't clear, however, to Schrödinger what these were waves of. He could characterize their mathematical properties, things like superposition, but he wasn't at all clear what they were representing. And it was actually 6 months later, in June of 1926, when another physicist, the German theorist Max Born, suggested that maybe psi was not a property of the electron per se, but was more about how the electron is likely to behave. Or as we now say, that the wave function is related to the probability that upon measuring that object, we'll get a certain outcome. as opposed to being something about how the object itself is sort of spread out in space or something like that. That psi was sort of meta. It was describing the likelihood to find an outcome. So we come back to this beautiful illustration of what we call the hydrogen wave function. This is for a single electron in a single atom of hydrogen. We can plot the square, the absolute square of that wave function for different states of the electron in the hydrogen atom. And the darker colors correspond to greater likelihoods, higher probabilities, that if we were to try to measure the location of the electron, we'd find it in the darker regions rather than the lighter ones. And it varies with the state and so on. So we may get these beautiful pictures. The structure of the hydrogen atom is really a play of probabilities. We can calculate to great precision. What we're calculating is not where is the electron now, it's what's the likelihood we'd find it there if we went to look. That was at least Max Born's suggestion. So soon after that, another physicist whose name will probably be familiar to many of you, the young British mathematical physicist named Paul Dirac, really put this on an even more formal mathematical footing. He was following this work very closely. He was basically a grad student or a recently graduated PhD at the time, very young. And he realized that these quantum waves that Schrödinger was describing could be treated really just like vectors. And we teach vectors to our students all the time. He was in some sense trying to make it look more familiar mathematically. These were vectors in an abstract mathematical space, and I'll say more about that in a second. But the way that we could manipulate them would be the way we manipulate vectors all the time, even in ordinary three-dimensional space. And so what superposition implied, this notion that waves could add and still be a proper solution, Dirac said that's like how we handle vectors all the time, that our quantum state, which we'll write with this symbol psi, could be some weighted sum, that's like the superposition, we're adding them together with different weights, of quantum states that correspond to very specific properties. If we measured the electron and asked about this property, it would have this value, or maybe that value, or that value, and we weight these vectors in the abstract space by these constants. See, these are just numbers in front, just simple complex numbers, but they're just numbers, not functions. And so again, the analogy is to how we treat vectors all the time in ordinary three space. We have some arbitrary vector, we can call it capital A, and as you know, and your students know, we can find the projections of that vector on various axes. And so the idea here was that this abstract sounding quantum state was basically a series of kind of projections on these basis vectors in terms of which we could describe the more general quantum state. And because of superposition, we can add them up this way. That's all that we're doing here. And in fact, in some instances, the mathematics for quantum theory is actually even easier than for vectors in three-dimensional space. A system that we use, that we think about all the time, and probably again familiar to many of you, would be the system for spin, the intrinsic angular momentum for a particle like an electron. And here we actually only have two independent directions, not even three. In ordinary space, we have to worry about, X, Y, and Z, east, north, and up. But for some quantum systems, we only have two directions to worry about, in a sense, up or down. So the spin of an electron could either align exactly along some reference directions, along some magnetic field, or exactly opposite and nothing in between. So we only have two directions to worry about. So these are each valid quantum states. They are appropriate solutions of the quantum equations. And therefore, Dirac said, building on Schrödinger, we can build more general quantum states by adding them up, by doing this superposition, a weighted sum of this quantum state and that quantum state, and they might have different weightings in front, even though each state on its own is incompatible with the other. These are perpendicular. And we never find an electron that is somehow both up and down. We find either spin up or spin down. So the properties are incompatible with each other. And yet, according to Dirac, we could use this math-like vector analogy to build perfectly valid quantum states out of pieces that sort of otherwise we think might not fit together. So if we consider that state, this superposition, we can now combine that with Max Born's suggestion that these quantum states psi are somehow related to probability. And then we can use this formalism to say things like, what are the odds? What's the probability that if I measured the spin of this electron, I would find it to be spin up? That's related to this square, the absolute square of this probability-like quantum state. In this case, the square of that piece. That's the kind of projection along the spin up state. What's the probability that when I perform a measurement, I'll find the electron to have been spin down? It's the sort of the square of the other component. And so every time we measure the spin of the electron, we always get a definite result. I think that's really important. We never find it washed out or fuzzy or in between. We never find it spin, 38.7 degrees. It's straight up or straight down. What varies is the likelihood to get either of those definite answers. The probabilities need not be all one or the other, but the outcome is either all up or all down each time we perform a measurement. And so that's, on the one hand, I think very powerful, very clean, sometimes, as I say, even easier mathematically than treating vectors in ordinary space. And yet it comes, or we've snuck in a bit of a cost, or at least a surprise. According to people like Max Born, Paul Dirac, and Niels Bohr, and of course soon many others, what these equations of quantum theory tell us are probabilities and not definite outcomes. The equations seemed at least to offer no way to know in advance whether the electron, the particle, really had spin up or spin down. We could calculate the odds of what we would find upon performing a measurement. And that was a pretty significant change from how we used to think about Newtonian physics or electromagnetism or other areas that have been highly successful. Niels Bohr went even further, and he said, what if it's not just that we don't know, what if the particle actually had no definite value, say for its spin, until we performed a measurement? So it's not that it was really spin up and we just didn't know and we thought, well, it's 50-50 odds or whatever. What if the particle had no definite value of spin until we performed a measurement? And as I like to say, that's like saying that, you or I have no value of our weight until we step on a scale, which actually might be kind of hopeful these days after COVID. Maybe it would be nice to wish we didn't have a definite value of a weight. But either way, I think we imagine that as we walk around our house and maybe even the neighborhood, we probably have a weight even when we're not measuring it. And Bohr was saying for elementary particles and maybe even whole atoms, maybe they had no definite value, not just that we didn't happen to know what it was. So that's one of the kind of upshots of thinking about superpositions and probabilities with these cool equations, is that we start hitting up some differences from familiar physics and not only familiar ones. So I'm going to pause there. There's plenty of time for some questions, and I'll jump into the next part. Any questions on that part? All perfectly straightforward. People lost sleep over this, so it's okay. If we have other things to worry about these days. But
Peter, did I see a? There you go. Peter, jump in.
Sorry, I had to find that new hand. Thank you for that. As a chemistry teacher who touches on this just a little bit with the kids at the beginning of the school year, they're always so hung up on, is the electron always spinning up? Is the electron always spinning down? So we explain to them that it's probabilities and all that, and we just say up and down is opposite as opposed to up or down. But what you just explained was maybe it is actually up or down. So how could I better explain to the kids what's happening there?
Peter, thank you. That's a great question, Peter. So in a sense, it's a preview for the next part. So up to now, it seems like we could either say the electron has a real spin, and we just don't know which one it is. So we're ignorant because we haven't measured yet. It could be either spin up or spin down. It still shouldn't be anywhere in between, according to the equations, but we'll have some chance, some likelihood. If we then bring in our magnets and perform a bunch of measurements, then we could determine, do we measure spin up or spin down? As we'll see, even that gets us in trouble. So what I've told you so far is sufficient to say, we don't know yet. What that last quotation, or I should say the suggestion from Niels Bohr, is that actually even that is attributing too much definiteness to the electron. Bohr he wasn't proving it, he was stating that one way to make sense of these equations was not that the electron has a real value and we don't know it yet. Maybe the electron doesn't have a single definite value until we bring in the magnets, perform the measurement, or really hire the grad students. How do you really do experiments? You need more than magnets, you need actual people. So that's part of the question. And in fact, that's a great segue to the next part for the presentation. It's great.
Thank you.
Let's see, I'm going to try to get them in the order I see the magic hands popping up. Whoops. So it looks like on my list, Henry and then Jared, please. And then Anjali, if you, after that, how's that? Okay, so Henry, please.
Thanks, David. So I was wondering if you could give an example of an experiment where the theory and the result match to 12 decimal places.
Oh, yeah, good. Thank you, Henry. So the one that I was referring to, obliquely, I admit, is on measurements of what's called the anomalous magnetic moment of the electron. Or if you just Google the words magnetic moment, that should get you there. And that's a good opportunity for me to say, please feel free to email me even between sessions or after sessions too. There's a ton of stuff I'm going to throw at you or throw your way. And I would be delighted to, if questions come up, please don't be shy and feel free to email afterwards. I can send you more links and stuff. But Henry, more specifically, the numbers I was quoting on screen were both theoretical predictions and then experimental measurements of this. It's really a property of how an electron reacts to or behaves when it's placed in a magnetic field. And it has to do with both its own charge and its intrinsic angular momentum or its spin. It's a combination of this that we call the magnetic moment. And there's all kinds of wonderful, wacky quantum effects that go into that. And so that's why you have to worry about all these things out to 12, 13, 14 decimal places. That was the one I had in mind. There are other super precise measurements that have been conducted as well. That, to my mind, holds the record. But there are plenty that can get to parts per billion, if not parts per trillion, which is pretty amazing. Jared, please go ahead.
Hi, David. Thanks for joining us, and really appreciate it. My question, when I learned quantum mechanics back in college, was I did learn it through the electron. Mm-hmm. And in reading your book, I saw that you focused on the neutrino, and that was 3 states or flavors. Mm-hmm. So if you were looking at the math, would the third flavor be a third dimension in like the way you would carry out the probability states?
Perfect. The short answer is yes. And the longer answer is yes, exactly. It's exactly right. In fact, I'll come to that later today. We'll see that even on the screen. That's exactly right. So that would be like having an X, Y, and Z with which to describe our vector as opposed to only X and Y or up and down. That's exactly right. Yeah, awesome. Anjali, please.
Right. I just wanted to know that when you are talking about abstract space, is that the Planck's constant space?
Oh, thank you, Anjali. I guess we could relate it to that. Planck's constant, of course, is really a number. And in a sense, it sets a scale. It's a dimensionful number. So in human terms, it's minuscule. As you know, it's something like 10 to the minus 36 of the units that we would otherwise be familiar with. Whereas if I I calculated this, if I drop a grape from 5 inches and ask for the amount of energy it has when it hits the table, so it's at rest, it has potential energy, I let it go, it hits the table with a certain kinetic energy, and I measure that in units of the Planck's constant, it's like 10 to the 30, it's huge. If we're thinking about the scale of electrons or atoms, of course, it's the more appropriate scale to think about. But that just sets the scale in which we expect to find these quantum effects being really important. The mathematical space is really, it's a vector space. It just happens not to be vectors about sort of north, south, east, west, up, down. It's more abstract because we can talk about spins or about neutrino flavors or wide range of things. So the scale in which we expect to find deviations from the physics that we otherwise know so well, Newton and Maxwell and these things, that scale is just as you say, Anjali, set by Planck's constant. That's right. Rashidul, please.
Thank you. Thank you.
Thanks, Anjali.
Yeah, Peter talks about spinning. So this is a follow-up question, like the application of spinning now kind of been trying to made in quantum computing. So my question is how qubit can hold more information than bit using this weird feature of quantum mechanics and spinning of electron?
Yeah, wow, what a great question, Rashidul. Thank you. So the short answer is you're right. When we talk about qubits, and when I say we, I mean my colleagues. I'm qubit adjacent. I don't actually work in quantum computing, but a bunch of my friends do. So they really do mean things like a spin system. They can manipulate individual spins, either of electrons or spins within an atom and so on. It's kind of amazing to me. And they really do mean, is it either spin up or spin down? Or again, as we'll say more about soon, is it actually spending most of its time in sort of either and both? That's the superposition. And so by not forcing the qubit to be in one definite state at each moment, in a sense, we're, roughly speaking, taking advantage of both and letting the system explore both paths in parallel. And that can yield these kind of exponential speed ups in certain kinds of computation. That's very hand wavy. But the basic idea is by not forcing the system to be in either, a gate that's open or closed, the way that we think about ordinary computers, there's some electronic system is in either a 0 or a 1, but not both. And the qubit is in some sense both states for much of the time. And so you're sort of you're exploring the system through both possibilities and letting those percolate up. And so that yields, for certain kinds of calculations, not for any old thing, but for certain kinds of calculations, that can yield an exponential increase in the speed with which certain problems can be solved. And again, I'd be glad to try to send some references that would explain that better than I just did. So please feel free to send me a note afterwards. But it really does come down to qubits, just a fancy way of saying a spin system, a two-bit, two-answer system that's in a quantum superposition as opposed to a definite state. That's really all the name qubit means. Those are great questions. Let me jump into the next part. And again, we'll have another break in a few more minutes. These are great questions. But let me go back to the slides. Hopefully they're still there. Awesome. Okay. So again, we had a great preview with some of the questions just there about what's coming next. Some folks, including people like Albert Einstein, who had helped build quantum theory as we know it, they began to get a little uncomfortable with this notion of restricting the probabilities. And even when people like Niels Bohr made these even more radical sounding statements that maybe the electron simply doesn't have a value, not just that we don't know it. That started to really irk Einstein. He wrote, who's a very good friend, Max Born. Remember, Born is the one who introduced this probabilistic interpretation. 6 months later, Einstein wrote in this letter, his now very famous letter, which reads in part, quantum mechanics, he says, is certainly imposing, but an inner voice tells me it's not yet the real thing. The theory says a lot, but does not really bring us any closer to the secret of the old one. I, at any rate, am convinced that he is not playing at dice. That's a famous God does not play dice quotation. It comes from a letter that Einstein had written to his friend. It turns out Einstein had some other discussion buddies pretty soon as well. In fact, about a year after Schrödinger introduced what we now call the Schrödinger wave equation and the Schrödinger wave function, he got a big promotion. This was seen as pretty good stuff pretty quickly. So Schrödinger was hired to an even fancier university position in Berlin, the same city where Einstein was then working as well. They became close friends starting in 1927. They would talk about this stuff all the time and then continue their discussions by letter. And one of these letters that has survived, Einstein presses Schrödinger saying, do you think probabilities are enough? And he poses this very kind of simple sounding thought experiment. I think it's kind of like what Peter is pointing out even just in the questions. Einstein says to Schrödinger, what if someone has a ball, let's say a red ball, that's placed before we enter the room into one of two identical blue boxes, and then both boxes are sealed. So then we come in the room and someone says, describe the physics of the situation. We might rightly say there's a 50-50 chance that the ball is either in box 1 or box 2. But Einstein says that's the best we can do because of our ignorance. That's not how the world is. In the world, there's a real answer. The ball really is in either one of those two boxes. And Einstein presses, isn't it the job of physics to describe the world, not what we happen to know or not know yet? So his restricted probabilities struck Einstein as really, really insufficient or inadequate. Pretty soon after they became such close friends, both Einstein and Schrödinger fled Berlin. This is soon after the Nazis took over, starting in January of 1933. And so they continued talking, but now through a transatlantic letter. Schrödinger moved to Oxford and eventually settled in Dublin. Einstein moved to Princeton, New Jersey, the Institute for Advanced Study. And pretty quickly, you see their letters about quantum theory start to reflect some pretty scary worldly events. So they're still ostensibly talking about how to describe the universe of atoms and electrons, but look at how the analogies have shifted. I find this very chilling, actually. Here's a letter that Einstein wrote to Schrödinger after they both fled Berlin. He's now still trying to get at this question of probabilities. And he writes, Imagine there's a charge of gunpowder, not some ball in some box, right? Some gunpowder is about to explode. And it's intrinsically unstable, says Einstein, so that it has equal probability of exploding or not over the course of 1 year. And here's again the quote from the letter itself in translation. He goes on to say, in principle, we can describe this quantum mechanically with the Schrödinger wave functions. There's some state of the system. It obeys superposition. So it's just a simple sum of these basis vectors, if we want to speak technically. It's a superposition of the state in which the gunpowder remains unexploded and the state in which the gunpowder remains exploded, just like it could be the incompatible states of spin up and spin down. And again, from Einstein's letter, after the course of a year, this is no longer the case at all. Rather, the wave function describes a sort of blend of not yet and of already exploded systems, but that's the equations. That's too bad for the equations. In reality, he says, there's just no intermediary between exploded and not exploded. The probabilities might really just be our ignorance, but that's not how the world is, and shouldn't physics describe the state of the world? A week and a half later, Schrödinger writes back. Remember, this is transatlantic post in the 30s. It takes a while. It's not quite, retweets. So Schrödinger writes a long letter back after Einstein writes this letter about the superposition of the gunpowder. And this is the first instance of what comes to be known as Schrödinger's cat. This is from the letter, the private letter Schrödinger wrote then to Einstein a week and a half later. He now describes a new thought experiment. Confined in a steel chamber is a Geiger counter prepared with a tiny amount of radioactive uranium, so small that in the next hour, it's just as probable as not to expect one atomic decay. An amplified relay provides that the first atomic decay, if even one uranium nucleus decays, that will trigger the relay here, which in turn will shatter a bottle of poison, prussic acid, basically cyanide. This and, cruelly, a cat is trapped in the steel chamber. Again, thankfully, a thought experiment. No cats were harmed in the actual experiment. And in the letter, he goes on to say, after 1 hour, the living and the dead cat are smeared out in equal measure. It would be represented quantum mechanically by a superposition. These states are no more mutually compatible than spin up and spin down, but according to the equations of quantum theory, equations that Schrödinger himself had helped to introduce, this seemed to be the best that quantum theory could do to describe the situation, even though it struck, by this point, Schrödinger, just as it struck Einstein, as being really insufficient or inadequate. So Einstein writes back as soon as he could, right away, your cat shows that we are in complete agreement. A wave function that contains the living as well as the dead cat just cannot be taken as a description of the real state of affairs. And so there's an irony. Schrödinger then goes on to publish this in almost identical wording in a kind of popular science magazine. You can see it comes out in German, but he sends it in from Oxford. That gives you another reminder of how the world had changed. This was sort of the Scientific American of Germany, a kind of popular science magazine. And there's an irony. By about a decade into his own experience with quantum theory, Schrödinger himself had become just as skeptical as Einstein about the work that they each had done so much to put together, and in fact became an outspoken critic of it. So this cat paradox, which was now an internet meme and it's sort of invoked all the time, it was not introduced as a way to kind of teach these wonderful ideas of quantum theory. It was introduced as a critique to try to show the limitations of quantum theory, at least as seen by people like Einstein and Schrödinger, and in particular, this conjunction of concepts of superposition and probabilities. 50 years later, so going from 1935 to 1985, that's a long span of time, some other physicists introduced a way to try to test what had by this point had become kind of a thought experiment or a kind of philosophical debate. Either you like it or you don't. But by the mid-1980s, quite a long time later, Tony Leggett and Anupam Garg introduced a really clever experimental arrangement to try to test whether physical systems could really exist in this either or both and state, the superposition, or whether it had to really be one state or the other, even if we happen not to know it. This comes back again, I think, to Peter's question from before. So the idea of the Leggett-Garg work was to perform repeated measurements on the same object, but at different times. Measure the same property of the same thing, but over time, and then compare the outcomes, which sounds pretty innocuous, but bear with me, we'll see how this becomes actually a pretty powerful way to test. So they introduce what they called, we can call it dichotomic observables. That's a fancy way of saying properties that have only one of two possible answers, like spin up or spin down, yes, no, heads, tails. So the property we'll choose to measure could only be one of two possible outcomes. And then we'll compare the outcomes, produce a correlation function, which is just the product. If one was spin up and the other spin up, the product is +1. If one was spin up and the other spin down, the product is -1. If they're both spin down, the product's +1. So the correlation is just multiplying these answers together, even though we measured one at one time and one at a later time. Then they introduced this combination of those comparisons. And this is actually pretty, I think it's pretty ingenious and pretty unexpected. So put together this particular combination of the comparisons, compare the answers at ×1 and ×2, compare the answers at ×2 and ×3, and then subtract the comparison between ×1 and ×3. It looks pretty innocuous. If this object always had a definite value, even if we didn't know it, if the object always had a definite value, like the cat always being either alive or dead, then this combination has to obey a particular inequality. It can be no bigger than 1, no smaller than -3. And that's only on the assumption that the object always has a definite value, even if we don't know it. So it did not actually persist in a superposition. And so you can convince yourself with just do some trial and error. Remember, Q is just some random number, either +1 or -1. Say we're measuring spin or really even flipping a coin. Heads, heads, tails, tails, heads, tails, tails, whatever it is. Do that a gajillion times, compare the answers. If you choose this particular set, you'll find this combination is -3, difference is +1. Take a statistical average and you can convince yourself a little more fancy algebra, you'll see it should always fall within these bounds, within -3 and +1. Conceptually, what does that mean? It means that this quantum system, the system we're testing, it's as if it had a logbook with it or an instruction manual. So everywhere it zigged and zagged through space, it had a definite value for each of the properties we might choose to measure, even if we didn't measure them. It's like saying the electron had really spin up, we just didn't measure it then. We thought it had a 50% likelihood of being spin up, but it really had spin up. That's what it takes, that's the assumption that yields this Leggett-Garg inequality. On the other hand, quantum theory does not say that that electron really had a definite value of spin before we measured it. In fact, it says the likelihood to find either outcome travels like a wave. It's one of these wave-like quantum features that can have interference. And for many, many physical systems that we might want to describe, the quantum mechanical prediction for this correlation function takes a very simple form, the simplest wave you can write down, just a cosine. It'll depend on the difference in time. That's the prediction. That doesn't mean that's how it works in real life. That's the prediction from quantum theory. And so if that's the quantum mechanical prediction for these comparisons of some property, if we don't assume that thing has a real value in between measurements, then there should be scenarios by which this quantity K could exceed the inequality. You could get a Leggett-Garg parameter K that was larger than 1, whereas you should never find anything larger than 1 if the thing really had definite values even in between measurements. So now you have a showdown. Now you have an experimental test to try to say that objects go through the world in superposition or with the equivalent of a logbook where they had definite answers at each time. Okay? Again, let me pause there, take a few questions, and then we'll get to neutrinos. Any questions on that part? If there's nothing urgent, I'll press on because I realize I'm making a rookie teacher mistake and running long. So let me press on because I want to get to neutrinos because they're just pretty fantastic. If you do have questions that come up, of course, put them in the chat. I'd be glad to pause. All right. So what do we do now? We're armed with these ideas about probability and superposition, and we have this new way to try to tell the difference in the Leggett-Garg inequality. And that's where my friends and students and I tried to pick that up. So the main star of this story is actually not me. It's my friend Joe Formaggio, who's also a physicist at MIT. Joe's an expert in measuring neutrinos, these particles that I mentioned and that you had part of the reading about for today. He's a neutrino experimentalist. And it was really Joe's idea to try to test this inequality, this Leggett-Garg inequality, using not electron spin or other typical quantum systems, but actually using his favorite kind of particle, the neutrino. These interact, as I'll say soon, very, very weakly with ordinary matter. So they're a great kind of tool for these hypersensitive quantum-like tests. They don't get jostled from their quantum behavior very easily. So together with Joe, we worked with, Joe and I worked with two wonderful students, Mikola Mirskic and Talia Weiss. Mikola was then a graduate student in physics at the time. Talia was an undergraduate physics major. And we set out to use these neutrinos as our kind of microscope onto the quantum realm. Turns out neutrinos are incredibly ubiquitous. They are literally everywhere. Taking a cosmic census, there are 1 billion neutrinos in the universe for every atom of ordinary matter. They outnumber us by a wide margin. They don't outweigh us necessarily, they outnumber us. They interact so weakly with ordinary stuff of which we're made that tens of billions of them stream through each of us, each square centimeter the size of your own thumbnail, every second. And they don't even pause. They stream right through us. They stream through the entire Earth, most of the time without even having a hiccup. So they are everywhere and they interact extremely feebly with ordinary matter. So the fact that they're not easily kind of jostled is what presented us with this cool tool. Could we try to test for these alleged quantum properties over very long distances? Do these neutrinos behave like quantum theory says they should, or could they give us a hint that maybe superposition is not how the world works after all? So Wolfgang Pauli, another Viennese physicist, first introduced the idea of neutrinos in December 1930. He was very hesitant. It was just a speculation. He and his colleagues were puzzled by radioactive decay, which was still a relatively new topic. The puzzle in particular was they couldn't get all the energy to add up. The energy of the nucleus before decay didn't seem to balance the energy of the nucleus plus the stuff that came out after the decay. If they added up the energy of the electron that was emitted during a radioactive decay and the energy of the recoil of the nucleus, it didn't add up to the energy beforehand. And so Pauli's suggestion was maybe there's a second type of particle that gets spit out that we just hadn't noticed yet. So maybe the energy balance should be the energy of the ejected electron and of some unseen additional particle, eventually gets known as the neutrino. Add up that energy and that balances, and the recoil of the nucleus, and that should balance the initial energy of the state. And he says if this additional hypothetical particle has no electric charge, then maybe it makes sense why it hadn't been seen yet. It's very hard to detect neutral forms of matter, unlike electrons. So he said, maybe that's what's going on. 20 years later, there was still absolutely no evidence that neutrinos are part of the world. And so this was on someone's mind, Frederick Rhines, when he was a young physicist soon after the end of the Second World War. He was working at Los Alamos, working on next generation nuclear weapons after the ones that had been used on Hiroshima and Nagasaki in 1945. And he realized that these nuclear bombs should, at least according to nuclear theory, they should emit enormous numbers of neutrinos, many more than would ordinarily be in the area. These should be like neutrino factories. And he was in the business of building and blowing up nuclear bombs above ground, the era of above ground nuclear testing in the early 50s. So he proposed and actually got permission, which boggles my mind, to do the following experiment. Next time they're going to explode a new test device for a new kind of nuclear bomb, he would prepare a sensitive detector filled with a certain kind of liquid, basically like dry cleaning fluid, heavy hydrogen heavy liquid. And then as soon as the bomb went off, there would be some electronics, some triggering release to drop the detector in free fall down a very tall but narrow tower, underground tunnel. If he bolted it to the ground, it would have ripped apart by the shock wave. So he lets it go in free fall, and it lands on feathers and foam rubber. And then several days later, he and his colleagues would dig back after the surface level of radioactivity was modestly, safer, and then retrieve the detector and see if they caught any wayward neutrinos during this momentary flood of neutrinos. Well, it turns out a little more thought convinced him and his colleague Clyde Cohen they could actually do this slightly less dramatically by studying neutrinos that might be coming out of a nuclear reactor rather than exploding bomb. So still the nuclear stuff, but now in a more controlled setting. So they went and installed at the then brand new nuclear reactor in South Carolina, the Savannah River plant, which was not at the time producing power for electric, civilian use to power our homes. This was a reactor plant to make more fuel for more bombs, making both plutonium and tritium. And as a side effect, it was hypothesized to be making tons and tons of neutrinos as well. So there, again, with a tank, they were able to finally capture a few convincing glimpses of these, attributed them to neutrinos. So in 1956, 26 years after they were hypothesized, the first direct evidence that neutrinos are even part of our world was introduced in this pretty dramatic kind of Cold War setting. That led to another strange question, though. If a nuclear reactor on Earth produces lots of neutrinos, what about the biggest reactor we know, which would be the sun, the biggest reactor in our neighborhood? The sun, of course, is an enormous nuclear reactor. It should be producing even greater numbers of neutrinos. And according to the best nuclear theory at the time, it should be producing so many that they should be found, at least trace numbers, in enormous experiments deep underground, like this one performed by Ray Davis, a huge tank in a former gold mine in South Dakota. But what kept happening is Davis was finding 1/3 of the predicted number. So everyone said, well, your experiment's not sensitive enough. He performed some amazing calibrations and stubbornly kept finding 1/3 of the expected amount. So while this is going on, another physicist, a theoretical physicist named Bruno Pontecorvo, and I wrote about him again in the short piece for today, and some really quite remarkable biographies of him have come out recently. He suggested maybe there's more than one type of neutrino. What if there are 3 types? And this is coming back to the question I think Jared had asked earlier, someone asked earlier. If there are 3 types, there might be a mismatch between their properties. There might be 3 so-called flavor states, and that controls how they interact with different kinds of particles. But there also might be 3 different mass states, and they might not line up. So we might have a 3x3 superposition, where the states of definite mass, a solution to the quantum mechanics equations, this has mass 1, this has mass 2, this has mass 3, we have to build these quantum superpositions to figure out the way that an individual neutrino will interact with other forms of matter. So this side controls the interactions that a neutrino will have. Will it scatter off an electron? Yes, no, no. Will it scatter off a muon? Yes, no, no, and so on. So that's the so-called flavor states, each of which would be written as a superposition of distinct mass states, at least in principle. So then, like any of these quantum superpositions, there should be some waviness, some interference in the probability to measure a neutrino in one flavor state or another, like miniature Schrödinger cats. And in particular, the quantum mechanical prediction for a neutrino that begins in one flavor state at one time, what are the odds that neutrino will be measured to be in that same flavor state at a later time? It'll wiggle up and down like a wave. It'll go like sine squared. This is just a number, just a constant based on these constants C. But here's that wave-like, up and down over time. At least that's the prediction. And now that makes a lot of sense for Ray Davis's experiment. Davis was only sensitive to one of those 3 types. He was collecting all the electron neutrinos that came his way, but some of the neutrinos that began inside the sun as electron neutrinos had oscillated into a different form by the time they hit Davis's huge tank. And he just simply wasn't sensitive to them. So it's not that he was missing them per se, he was capturing this part of the entire sort of oscillation set of probabilities. More recently, 2 very large international groups have pursued this with even greater precision. Pretty amazing. These are both deep underground. The Super Kamiokande experiment in Japan is 15 stories tall, buried under a mountain 1 kilometer under the surface with 13,000 detectors. This is now getting big. The leaders of these 2 groups, the SNOW collaboration and the Super K, each shared the Nobel Prize in 2015 for more experiments on these neutrino properties. And then each of the groups together, several thousand physicists, shared something called the Breakthrough Prize in Fundamental Physics that same year, which was $3 million, split over 6,000 or 7,000 physicists. So my friend Joe is a member of the SNOW collaboration. He got a couple $100 out of this. He didn't win the Nobel Prize, but he got a share of a $3 million prize. His share earned him, as he said, a very nice bottle of wine. So by now, groups like Joe's and like Super K have gotten very good at measuring properties of neutrinos. So it was Joe's idea to turn that around. Can we actually now test quantum theory on the strength of how well we can characterize neutrinos? So that's what we tried to do using data from an experiment at Fermilab. So Fermilab, a different collaboration, makes neutrinos. They produce them not measuring from the sun. These are now Earth-made neutrinos by revving up protons with huge magnetic rings to very, very high energies and smashing them into a target, a well-chosen target. Among all the jump that comes spewing out of that reaction is a beam of neutrinos that then travel hundreds of miles through the upper Midwest. This is what the FAR detector looks like, very near the Canadian border, part of that Fermilab experiment, but now 735 kilometers north of where these neutrinos were produced outside Chicago. So it's deep underground, nearly a kilometer. It's a 5,000-ton detector. They have a closely stacked plates, steel plates, each of which is several tons, stacked super close together to make such dense material that every now and then one of the neutrinos will spark a reaction and be detected. It's extraordinary. The group, it's called the MINOS collaboration, had just begun publishing their own first data on these so-called oscillations. Neutrinos, in this case, begin in one flavor state, the muon state. They travel unimpeded through the upper Midwest, and then a handful actually trigger these detectors up near Canada. And they could do this for different energies of the neutrinos and so on. So what we did is took their data, with their permission, we used their data to put this in the form of a Leggett-Garg inequality. So let's be agnostic about whether the neutrinos really travel in superposition states or not, and use the strength of the new data to test their behavior. So the Leggett-Garg inequality concerns measuring the same system over and over again, but it's hard to measure a neutrino even once. So we actually performed comparable measurements on an ensemble, make a huge collection of neutrinos in an identical state. That's what the Fermilab group did for us, and perform measurements on the ensemble. Likewise, remember the Leggett-Garg inequality concerns measurements at different times, but no one was going to pay us to move a 5,000-ton detector, right? Where the time difference, it was fixed. The flight time from Chicago to Canada, we can't change that for these neutrinos. They're traveling basically the speed of light. But what we could do was go back to that quantum mechanical expression. Remember, the waviness is controlled by two terms working together. There's the frequency of oscillation and then the time delay. In our case, this time delay was fixed. We couldn't change that. We couldn't move the 5,000-ton detector. But this frequency depended on things like the energy of the neutrinos, and that was being varied thanks to the nice group at Fermilab. So we could test for this quantum interference-like effect because we could compare the behavior of neutrinos of the same flavor but different energies, and that still gives us this waviness term here. That's as if we looked at neutrinos of one fixed energy but different times. At least that was the idea. Okay, so I'm just about done. Come back to the Leggett-Garg inequality. It has this form for this interference. If quantum theory is right, if these objects travel in a genuine superposition, we should see this quantity exceed 1. If instead the system always has a definite value, even though we didn't measure it, then this combination should never pass 1. Okay, by putting the Fermilab data from MINOS into the form of this Leggett-Garg inequality, we could then ask, did the neutrinos have a definite value of their flavor, even if we didn't know it? It's like saying, did they make the upper Midwest journey with a logbook saying at every moment it has a definite value and it could just look it up? Right now I'm a muon neutrino, now I'm an electron neutrino, now I'm definitely muon neutrino. And if so, then this quantity should never exceed 1. Or were they making that multiple 100-mile journey in a genuine quantum superposition with no definite value in between, where it was neither, say, a muon neutrino nor an electron neutrino, but this strange quantum superposition, where it's either and both? And if so, then we should see clear evidence that this combination should violate 1, should be higher than 1. So you might have noticed that MINOS data had pretty significant error bars. Neutrinos are still pretty hard to measure. This is what their data looks like when you put it in the form of this parameter K. You still see some pretty big scatter with those real-world experimental error bars. What mostly our student Talia, our undergraduate, was able to do was some pretty sophisticated statistical analysis. Take every one of those error bars very seriously and show that even with those error bars, even with the wiggle in the data, we were measuring significant violations of the Leggett-Garg inequality by more than 6 standard deviations. What that means is that this was violating the sort of no superposition rule to better than 1 part in a billion, meaning the odds that this was due to statistical flukes was less than 1 part in a billion. The evidence is overwhelming that the neutrinos are traveling hundreds of miles in no definite flavor state at all. They're behaving like Schrödinger's dead and alive cat. It's not that it was alive and then died. For not even 1 whole year, this was the world record holder for the longest distance test of quantum theory. And I'll talk next time about the group that beat us merely 11 months later. It's another absolutely beautiful experiment. So let me wrap up. Again, I apologize for running long. So even though these individual quantum states might correspond to incompatible properties like spin up versus spin down, the equations tell us we can construct a valid quantum state by simply adding them together, a weighted sum. That's what superposition means. But that comes with it some of this baggage that sometimes makes us feel uncomfortable, like Einstein and Schrödinger. That means we're stuck, it seems to me, we're stuck calculating probabilities of superpositions and not saying the world has that property now, but rather it might have that property when we measure it. That's a very different way of handling things like vectors. And so rather than simply assume that that's the case, if it was enough to make Einstein uncomfortable, it's worth asking some follow-up questions. We could use now modern techniques like neutrino oscillations to test this and ask, did these neutrinos travel in a genuine quantum superposition, or could we say they had a real value that we just happen not to know? The overwhelming evidence suggests they're traveling in quantum superpositions. And so the next week I'll talk about quantum entanglement, which is even more strange. Lastly, and again, I'll make sure you can get a copy of these slides, but these are some books that I find very good, recent books by a number of friends and colleagues that are very accessible that you might enjoy and frankly your students might enjoy. Almost No Mathematics. And also for those, for yourselves or for your students who are maybe a bit more ambitious, we have some pretty amazing resources now available entirely for free online, which I didn't have when I was a kid because there was no online. But one I want to highlight is from MIT OpenCourseware, entirely free open access, no charge at all. There are hundreds, probably thousands of courses available. The one I want to highlight for this set of discussions is a course on Quantum Physics 1, the first course we teach to our own undergraduates on quantum physics. And you can go there entirely for free, get the full set of lecture notes, videos of all the lectures by a really marvelous teacher, my colleague Barton Svebak, all the problem sets and more. So there's many available resources on the web. I want to highlight this one because I think it's especially high quality. And that does involve a bit more mathematics, I think well within reach for some of your students. These books are much more accessible and frankly quite fun. So let me pause there again. My apologies for running a bit long. I'd be glad to stay on if people have some more questions.
Thomas, jump in.
Hi, thank you for the lecture. I read, I think a year ago, about a fourth flavor of neutrino. Could you tell us a little bit more about it and how it would affect all you presented to us so far?
Great, Thomas, thank you. Yes, so it's not confirmed, but it is a long-standing question. You're absolutely right. Whether there might exist additional flavors, a fourth, maybe a fifth. If so, it would have to have pretty different properties even than the three that we know, which are themselves pretty strange. It would have to be what's called a sterile neutrino, which means it interacts even less with other forms of ordinary matter. So one hypothesis is, could this be a form of dark matter? Could it answer more exotic questions about astrophysics? It's an open question. Whether it's even been detected is frankly still unclear, and I might even say controversial. Some people think the evidence is quite strong. Others say, let's be more cautious. So it's certainly not definitive, but many of my dear friends are on the hunt for it. That's an area of very lively research. Would it change our conclusions? It really wouldn't. In the energy range that the MINOS experiment focused on, the dominant conversions are between only two of the three known flavors anyway. Or let me put it another way. What we're really testing is whether the neutrinos are detected in a particular flavor or in other, where other could be any other kind of neutrino. And so in that sense, for this kind of experiment, we're open to whether there's two other types or three or four. Our other collaborators are trying to design experiments where it matters if there's only two other types or three. And that's what gets to I think, the point you're asking. For the particular data analysis we were doing, I don't think it would have been affected by if there really was a fourth neutrino. But it's a great question. It's definitely a point of real live research to this day. Ben, please.
Thank you. First of all, thanks for everything. My mind is a little bit blown, even though I think I knew much of this. But my question is, I vaguely remember when they were, talking about things about neutrino oscillation, that it was related to whether or not neutrinos had, mass or rest mass. And that they were trying to figure out whether neutrinos had mass, and if they didn't, because I can't remember which it was, but I think it was like if they had mass, they couldn't oscillate, but since they oscillate, then they shouldn't have mass. I don't
Very
think
close. You were right until that very last part is the opposite of that. But you're right. But that's what's at stake. That's absolutely right. That's why those team members, the team leaders, won the Nobel Prize. Is that they demonstrated definitively that neutrinos have mass. If they had zero mass, which had been the assumption all along, then these oscillations should be impossible. And what really happens is, if a particle has absolutely no rest mass, like a particle of light, for example, like a photon, then for that particle, in a sense, there's no clock. Its proper time never advances. We could watch it zip past us. In our rest frame, it clearly travels from A to B. But if you could snap a GoPro on the photon, but if you could see it from the photon's point of view, it would never see time advance. Kind of like living in pandemic, maybe, I don't know. And so if neutrinos are like that, if neutrinos have no internal clock, then how could they switch? Oscillation is a change over time. That's, again, the kind of hand-wavy argument for why if they're identically massless, you should never see this, this oscillation. Whereas if they have even a small mass, in fact, it could be vanishingly small, but if it's a non-zero mass, then they have a clock, right? Then they will have a measurable time, even from their point of view, from their reference frame. And if they have different masses, then you can have all these interference effects and the rest follows. So the Nobel Prize in 2015 was for definitive proof that neutrinos really have mass, even though we still don't know what the mass is. What we can do is measure the difference between the mass states. We can measure the gap, because that determines the rate of oscillation. Their absolute masses fall out of these equations for these kinds of experiments. We can tell that omega term is sensitive to the difference in masses, and now we can measure that quite precisely. And when I say we, I mean other people, but my colleagues. So we know that they have non-vanishing mass, they have a clock, and we can measure the difference in masses pairwise, M1, M2, M2, M3. And even that was pretty new. And that was a big deal because the standard model doesn't include their mass. And so the otherwise incredibly successful quantitative model for all the elementary particles just assumes they have no mass at all. So that's the first hint in 50 years that the standard model itself really isn't complete. So that's partly why it was such a Nobel Prize winning kind of worthy thing. Matt, please.
So the one thing that has always bugged me about all of this is what causes the collapse of this wave function. Is that you've got these particles traveling and they're in this superposition, but what step actually causes the collapse there? Is it an interaction with any other particle, or is it, you get my question.
I do. I can't believe this bothers you, man. It's such an obvious, I'm teasing. It's totally not obvious. It's a huge, huge, huge conundrum, and you are in exceptionally good company. If you want to get a bunch of seemingly mature adults to scream at each other, we now know several ways to do that in the broader world. If you select your adults carefully and only get certain quantum physicists, you'll get that reaction. And the reaction is, explain why the wave function collapses. They will scream at each other. I've seen it, believe me. And so there are a number of let's say, semi-compelling semi-answers, and around which the community is still not coalesced. Our wave function is not yet collapsed. And there are different ways of trying to account for it. And there are even some might make some modest experimental predictions, and there are constraints on certain versions of that. So it's not entirely hopeless, but it's pretty wide open still. And the answers range pretty broadly. And I won't go through all of them now, but just to say it's a live issue. And again, if you email me, I'd be glad to send you some additional links and resources. And some of the books I mentioned actually focus on this question pretty directly. Actually, those popular books at the end, some of them look at this quite squarely. So you get more insights there. This is where things like the so-called many worlds hypothesis comes in. One hypothesis, which I don't particularly follow myself, would be that in some sense, the wave function never collapses, just it splits into branches, self-consistent branches, including like us and our memories and our consciousness. And so it's as if the entire universe kind of duplicates in near identical copies, in one of which I saw the electron being measured spin up, in the other which the other me saw the electron being measured spin down, and they're totally causally disjoint. So you can make these kind of self-consistent stories that sound a lot like, kind of Star Trek episode or You Run With It. I have very dear friends, including my own PhD advisor, with whom I now run a research group, who thinks that's the best bet. I don't know, but I know smart people who advise that. Equally smart people in my mind advise things more like what you were saying, Matt, that it's interactions with other matter that will decohere, that will collapse it by physical scatterings. Then the question is, well, how many do you need and how do you know? So it's not a straightforward question. I'll stop there, or else I'll talk for another 8 hours. But that's that is a huge question. What I liked about our experiment here is that it sort of didn't matter. If the detector went click, I don't have to know why it went click. Did it find a muon neutrino or other? And so and same with the experiments we'll talk about next week, those in some sense sidestep the thorniness of the measurement problem, but it doesn't make it go away. It certainly doesn't answer it. It's a great question, Matt. Thank you. Rishido, please.
Thank you. So the neutrino was discovered by two scientists, Clyde Cowan and Frederick Rains in 1956.
That's right.
Clyde Cowan did not live enough to win the Nobel Prize, much the same way Hawking did not live enough to share the Nobel Prize with Penrose.
Yes.
Why it took Nobel Committee 40 years from 1956 to 1995 to recognize?
Thank you, Richard. The short answer is I don't really know. I agree with you that, and these are not unique instances where this has happened, as we now know. You know, all I guess I'll say is that the Nobel Prize, like any human endeavor, is done by people, right? And so people could either make mistakes and or have their favorite preferences or who knows what. But it's not exactly a popularity contest. I'm not trying to say that. But the range of human ingredients that go into these decisions are many. And so I guess that's the best insight I have there. But I agree with you. I think it was the evidence was compelling long before the prize was given. I think that's certainly right. Peter, please.
Thank you, and also thank you for the coursework resource. There's a lot of kids, especially this year, that have been asking for lots of enrichment, and this seems organized and very, very well put together. So thank you. But I have to push you on this spin up, spin down thing because you're in front of us. So try to put your best like high school teacher hat on.
Yeah.
So we say to them, all right, spin up, spin down. And I say, well, it is actually spin up and spin down. And then they say this, Mr. D'Amico, if electrons have all the same charge, how could all of them be going, or half go spin up and spin down, and the matter just doesn't go poof? That's what I do. I go hand wave,
Yeah.
Lots
So
of calculus.
why do they worry that the matter would go poof? Now I'm puzzled why they worry about that. There are funny things to worry about, but why would they worry about that, I wonder?
So the thing that I find hard with high school students is that they don't have the capacity to imagine in the abstract with this.
Yeah.
And so we talk about opposite charges and same charges. Why do the electrons, if some are going up and some are going down, and as if it's actually up and down, won't all of that interference with each other not just make them repel and overcome the protons attracting them?
Okay. Oh, thank you, Peter. I see what you mean. So in one sense, you could start an answer. Maybe you do start an answer by saying that. To start with an analogy to a different system that we can visualize better, like the solar system. The sun has an enormous mass. It's exerting a force on the Earth all the time. Why doesn't the Earth just fall right into the sun? Just like the protons are exerting an attractive force on the electron. Well, it's not, the Earth doesn't fall right in the sun because it has angular momentum and there's a stable path. There's a kind of balancing point, as you know. And so in some sense, we can get pretty far along the way, not all the way, but pretty far along to start this discussion by thinking about an electron, kind of like a little planet Earth circling the nucleus, which is kind of like the sun. Now, of course, that breaks down many ways if we try to push that analogy too far. But the idea is that there exist stable states, not any old state, but stable configurations in which the electron does not fall right into the proton, just as the Earth doesn't fall right into the sun. And that says it really is a pretty close analogy. It's the same mathematical form for the attractive force. Then for the electrons repelling each other, There are other things that go on which also get very hard to visualize, I mean, to be sure. But things like the Pauli exclusion principle, which has no analogy in the planetary, in the solar system example, right? But that, it's almost like that exerts a force that affects the behavior of these electrons, where an electron that is spin up and in the one location in space can't be zoom bombed, can't have another electron in the same spin come join it. If the spin's opposite, okay, now they can share that space because they don't have a complete list of the same properties. They've learned to share, right? And that leads to different kinds of that, because thankfully then we have the whole periodic table. We get stable shells and all the rest that you know so well and talk about the students. So there are things that break the analogy with the solar system. But for the why don't they all just fall into the nucleus? I think there it's the importance of the angular orbital angular momentum as opposed to the spin angular momentum that plays a dominant role, at least. If that helps.
Yeah, and it's funny. Ironically, if we get to quantum numbers and they could actually put definite thing on that, they're like, oh, okay, I get it. It's fine.
Right.
So,
and then it becomes just accounting. Like, oh, I get it. I had this and this and this and this, but we've given up, like a picture in our heads, at least I have, of a kind of physical motion through space and time. Now, that's a pretty hard trade-off, and I agree with for high school students, for any of us, I think. But in some sense, why do we have confidence in that very abstract mathematical framework? Partly because of these other things like I was describing, because we can test other parts of that, some of them out to parts per trillion. So even though it looks like either a kind of a shell game, or how could that be, or how do you know?
Thank you.
Yeah, my pleasure. Henry, please.
Thank you. So I was wondering about the cat.
Yeah.
Presumably Schrödinger takes Einstein's gunpowder thought experiment and returns with a cat because the cat has some kind of experience. So and it's kind of like en route to a human. So, and if there are all these gorgeous experiments that show that superposition holds until the measurement is made, what if it was me in the chamber? What is my experience while y'all are observing it from the lab?
Super great. Henry, do I remember right? Do you teach English? Is that right? Or theater? Or is it?
No, I'm a science teacher. I also teach some cognitive science, though. This comes up, and I'm interested in metaphysics too. So
I read the bios quickly. I forgot. I thought we had. Anyway, I want to say that you're an exceptionally good company, because what you just described offhand was articulated in almost exactly the same way by a Nobel laureate named Eugene Wigner in 1961. So yes, he was trying to take this to the exact same kind of level of almost a kind of reductio ad absurdum argument. And so this is often now called Wigner's friend, is the thought experiment. So Wigner thought the answer was it requires something like consciousness to collapse the wave function. That's not a highly popular model today, but super smart Nobel laureate in physics was saying this in their 60s at least, which can give us pause. And then the question is, well, then what's conscious enough? Is a cat conscious enough? How about an amoeba? Like you can play that game, right? What most physicists tend to think about these days, coming back to Matt's question, is that it might be something more like, how many moving parts do you have? So a cat not only has something like consciousness, but maybe more relevant for this, that it has, several times Avogadro's numbers of atoms in it, which comes back to a version, I think, as Matt was describing. Is it the interaction of so many moving parts that washes out this quantum coherence? And that's quite a popular notion among the physicists today, which is different from having to say the world splits or some other. It's another part of the proposed explanation. It's often called decoherence, which is a fancy way of saying if you have lots of moving parts, they'll kind of wash out. They'll wash out this strange quantum superposition on a characteristically short time scale. So when I talked about the neutrinos, I talked about a macroscopic test in one sense. We tested quantum coherence over hundreds of miles. And for 11 months, that was the record holder. But it was still only single particles at a time. It was microscopic if you count the moving parts, what we could call the degrees of freedom. So it's super microscopic, one particle at a time over human distances. The other challenge is how many moving parts can you get to do a quantum coherence, to stay in a superposition state. The record holder there I think is buckyballs, C60 molecules. So that's gargantuan compared to an electron, many millions of times more massive than electrons. colleagues of mine, in fact, one of my co-authors, well before I started working with him, I think it was his group that holds that record for getting pairs of C6 carbon-60 molecules to quantum interfere, which is a version of showing that they were in this kind of superposition-like behavior. So that's pipsqueak compared to a cat. That's nothing compared to you and me. It's unbelievable, right, compared to individual electrons or neutrinos. So the other challenge is macroscopic in terms of how many parts, how many degrees of freedom. And there, people have not yet done things like viruses, which are maybe marginally alive, but they're getting closer, right? Technologically, maybe they could get viruses to quantum cohere. And that's still not answering the question about you or Eugene Wigner saying, did a smart human have to, perform a measurement? But it'd be a way of asking, does anything change as the number of interacting parts rises? So put it that way. And that's the kind of frontier that some of my colleagues are chasing.
Thank you.
So I see people have leave. I'm sorry for running long. I'm happy to stay longer, but obviously please feel free to hop off as you need. James, please.
Yeah, I just have a short follow-up question to Henry's. Like you mentioned the buckyball, and I heard that when I was an undergrad. I was like, wow, that's pretty wild. I'll remember that one. But I thought at the time, and now I'm thinking again, like, was that experiment done with completely, like totally indistinguishable buckyballs? Like every single carbon atom was a C12 atom, and like every single component. What would happen if you like, oh, well, there's a C14 here. Like, do those just like, they're classic billiard balls then?
That is a great question, James. So the short answer is I don't know. I'd have to go back to the paper myself. Let's see. Does it matter that they were indistinguishable? Is what you're asking about? There must be some tolerances where for the kind of experiment they were doing, it was okay. Could we get other things? I think we can get things to quantum interfere that need not be identical in every one of their properties. So for example, it's very hard, it gets harder. But other colleagues have gotten distinct beams of light to interfere. Well, they have to do pretty good, careful controlling. It's a great, James, the short answer is I don't know. And let me try to get back to you and find out for next time. That's a great question. What are the kind of tolerances for whether these objects are literally quantum indistinguishable or not? Really interesting. I hadn't thought about that. I don't know. Yeah, thank you.
Excellent. Oh my gosh. Well, with that, let's wrap up for today. Thank you so much, Dr. Kaiser. This has been just fascinating. And thank you to all of you who have been here to help enrich the conversation. Can't wait till next week. Look forward to seeing you all then.